Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Joseph-Louis Lagrange, a name synonymous with elegance and power in the annals of mathematical physics, emerged from a world grappling with the limitations of existing methods in mechanics. Born in Turin in 1736, his early life, though marked by modest beginnings, foreshadowed a brilliance that would reshape our understanding of the physical universe. His initial exposure to mathematics stemmed from a chance encounter with a paper by Edmund Halley, piquing his curiosity and setting him on a path of relentless intellectual exploration. This early fascination quickly blossomed into a profound mastery, fueled by a prodigious talent and an unwavering dedication to unraveling the complexities of the natural world. The intellectual landscape of Lagrange's youth was one of vibrant transition. Newtonian mechanics, though revolutionary, relied heavily on geometrical intuition and individual problem-solving techniques. While remarkably successful in explaining a vast range of phenomena, this approach lacked the unifying power and systematic framework necessary to tackle increasingly complex systems. The solutions to many problems, often ingenious and insightful, remained scattered and lacked a cohesive, generalizable form. This fragmented landscape posed a significant barrier to progress, hindering the development of a truly comprehensive and predictive theory of mechanics. Lagrange's early work directly addressed these limitations, laying the groundwork for a more abstract and analytical approach. He recognized the inherent power of calculus, a tool still relatively new in his time, to provide a more rigorous and systematic framework for describing motion. This intuitive leap, to move away from the predominantly geometric methods of his predecessors, marked a significant departure and foreshadowed the profound change he would bring about in the field. Lagrange understood that the language of calculus could capture the essence of mechanical problems with greater precision and generality than geometric constructions alone could achieve. This shift toward a more analytical perspective was crucial in paving the way for the sophisticated mathematical tools he would later develop. His early publications, already demonstrating a remarkable grasp of advanced mathematical concepts, captivated the attention of leading figures in the scientific community. His correspondence with Euler, one of the giants of 18th century mathematics, marked a turning point, establishing a collaborative relationship that would prove immensely fruitful for both men. Euler's influence, while undoubtedly substantial, served only to amplify Lagrange's own innovative thinking, shaping a unique voice within the scientific discourse of the time. Euler, already a master of the calculus of variations, provided a fertile ground for Lagrange's budding genius to flourish, and in turn, Lagrange's contributions would profoundly enrich the field. The problems Lagrange confronted in his early career were not simply theoretical exercises. The need for more powerful mathematical tools was driven by practical demands, arising from attempts to understand and predict the motion of celestial bodies. The complexities of planetary orbits with their intricate gravitational interactions presented a formidable challenge to existing methods. The limitations of purely geometric approaches became increasingly apparent as scientists sought to model more complex systems. The need for a more elegant and general approach was becoming undeniable. Lagrange's early contributions, while perhaps not fully mature in their final form, were pivotal in establishing the groundwork for his later, more comprehensive work. His early exploration of analytical methods, his adoption of a more abstract mathematical framework, and his crucial interaction with leading mathematicians of his era, all of these elements converged to prepare the stage for his most influential achievements. The seeds of his future success were sown in this period of intense intellectual ferment, a time of transition and exploration that Lagrange, with his unique combination of talent and vision, would ultimately transform. The enduring legacy of this early phase lies not only in the specific results he obtained, though these were quite significant in their own right, but also in the foundational shift in perspective he fostered within the scientific community. The move towards analytical mechanics, a shift away from relying solely on geometrical intuition towards the power of abstract mathematical tools, revolutionized the way physicists and mathematicians approached problems of motion and dynamics. This analytical approach, a direct consequence of Lagrange's early insights, remains a cornerstone of modern physics and engineering, underpinning many of the most sophisticated models and simulations used today. From aerospace engineering to the design of complex mechanical systems, the analytical methods championed by Lagrange continue to drive progress in countless applications. His early explorations not only solved problems of his time, they changed the very language in which the problems of mechanics would be formulated and solved. The conceptual framework Lagrange established continues to shape our understanding of the universe, a testament to the enduring power of his foundational ideas. The transition from a primarily geometrical understanding of mechanics to the more abstract, analytical approach was not merely an incremental improvement, it was a paradigm shift, and Lagrange was at its very heart. Building upon these foundational insights, Lagrange's Mécanique analytique, published in 1788, stands as a monumental achievement, a testament to his unparalleled ability to synthesize and systematize the vast and often disparate body of knowledge concerning mechanics. The work addressed a pressing need within the scientific community, the lack of a unified, elegant framework for solving problems in classical mechanics. Prior to Lagrange, the subject was a patchwork of methods, often relying heavily on geometrical intuition and ad hoc techniques. Newtonian mechanics, while revolutionary, frequently led to complex and cumbersome calculations, particularly when dealing with systems involving multiple bodies or constraints. Lagrange's genius lay in his ability to recast mechanics in a purely analytical form, dispensing with the need for geometrical diagrams and relying instead on the power of calculus, specifically the calculus of variations. This innovative approach allowed him to formulate a set of general equations, now famously known as Lagrange's equations, that could describe the motion of any mechanical system, regardless of its complexity. The core of Lagrange's method lies in the principle of least action, a principle stating that a system's evolution will always follow a path that minimizes a certain quantity, the action. This action, a function of the system's configuration and its time evolution, is expressed as an integral involving the system's kinetic and potential energies. By applying the calculus of variations, Lagrange elegantly derived his equations, which provide a powerful tool for determining the system's trajectory. These equations, expressed in terms of generalized coordinates and momenti, offer a significant advantage over direct application of Newton's laws, particularly in systems with constraints. The elegance and power of Lagrange's approach are exemplified by its ability to seamlessly handle systems with constraints, a persistent challenge in Newtonian mechanics. Instead of dealing with the forces of constraint directly, Lagrange's method allows one to incorporate these constraints implicitly into the system's generalized coordinates, thereby simplifying the problem considerably. This technique, a hallmark of Lagrangian mechanics, significantly reduces the complexity of the calculations, revealing underlying symmetries and simplifying the analysis of intricate mechanical configurations. Consider, for instance, the problem of a double pendulum. Newtonian approaches quickly become algebraically cumbersome, while Lagrange's equations provide a far more tractable pathway to solving for the system's motion. Moreover, Lagrange's work introduced the concept of generalized coordinates, a pivotal advancement that liberated mechanics from the limitations of Cartesian coordinates. This generalization allowed for the description of systems using coordinates tailored to the specific problem at hand, often leading to significant simplifications. The introduction of generalized coordinates, in conjunction with Lagrange's equations, facilitated the analysis of a wide range of mechanical systems, from simple pendulums to complex linkages and rotating bodies. This flexibility extended the reach of analytical methods to problems previously considered intractable. The implications of Lagrange's mécanique analytique extend far beyond the immediate solutions it provided. The framework established by Lagrange. Lagrangian mechanics became the foundation for Hamiltonian mechanics, developed later by William Rowan Hamilton. Hamiltonian mechanics, a reformulation of Lagrangian mechanics, introduces the concept of Hamiltonian, a function of the system's generalized coordinates and momenta. This reformulation provides a different, yet equivalent, perspective on the system's dynamics, offering valuable insights and leading to further simplifications in various contexts. The Hamiltonian formalism is particularly useful in advanced areas of physics, such as quantum mechanics and statistical mechanics. The enduring legacy of Lagrange's work is evident in its continued relevance to modern physics and engineering. Lagrangian and Hamiltonian mechanics remain fundamental tools in theoretical physics, providing a powerful framework for analyzing a vast array of physical systems, from celestial bodies to elementary particles. In engineering, these methods play a crucial role in the design and control of complex mechanical systems, robotic manipulators, and aerospace vehicles. The elegance and efficiency of Lagrange's approach have made it an indispensable tool for both theoretical investigations and practical applications, solidifying its position as a cornerstone of modern science and engineering. The analytical techniques he championed are not merely historical artifacts. They are the very language in which many of today's most advanced problems are formulated and solved. This enduring influence underscores the profound impact of Lagrange's intellectual contributions. The systematic nature of his approach, his ability to unify disparate concepts, and his mastery of mathematical tools all contributed to a lasting legacy that continues to shape how we understand and interact with the physical world. His work is a testament to the power of abstract thought and the enduring relevance of fundamental principles in the advancement of scientific knowledge. The systematic elegance of Lagrange's analytical mechanics, so powerfully demonstrated in his work on the dynamics of rigid bodies and fluid motion, found its most dramatic expression in his profound contributions to celestial mechanics. The heavens, with their intricate dance of planets and stars, presented a challenge of unparalleled complexity to the scientific minds of the 18th century. Newton's law of universal gravitation, while a monumental achievement, provided only a partial solution. Predicting the precise movements of celestial bodies, especially when considering the gravitational interactions of multiple bodies, remained a formidable obstacle. This was particularly true in the case of the three-body problem, a seemingly intractable puzzle that captivated and frustrated generations of mathematicians and astronomers. The intricate interplay of gravitational forces between three celestial bodies, for example, the Sun, Earth, and Moon, defied simple analytical solutions, leading to complex and unpredictable orbital patterns. Lagrange, with his characteristic blend of mathematical ingenuity and physical insight, approached this problem with a novel perspective. He recognized that a purely Newtonian approach, reliant on direct integration of equations of motion, was likely to prove fruitless for such a complex system. Instead, he turned to the power of analytical methods, employing a combination of differential equations and series expansions to approximate the solutions. His work on the three-body problem not only yielded significant advances in understanding planetary motion, but also introduced fundamental concepts that continue to resonate in modern astrodynamics. He demonstrated a remarkable ability to extract essential features of the system's dynamics, even when precise, closed-form solutions were unattainable. Central to Lagrange's success was his development of perturbation theory, a powerful technique for approximating the solutions of complex dynamical systems. This approach involved expressing the system's equations of motion as a sum of simpler solvable parts, and then iteratively refining the solution by accounting for the effects of smaller, perturbing forces. In the context of celestial mechanics, this meant breaking down the complex gravitational interactions of multiple bodies into a combination of simpler two-body problems, with corrections added to account for the influence of other bodies. The ingenuity of this method lay in its ability to handle the inherent non-linearity of the gravitational force, a feature that had previously stymied simpler approaches. The development of this methodology was a landmark achievement, transforming the way astronomers approached the problem of predicting planetary motion. Moreover, Lagrange's investigation of the three-body problem led to an extraordinary discovery: the existence of Lagrangian points. These are specific locations in the orbital plane of two massive bodies, where a third, much smaller body can maintain a stable relative position. These points, sometimes referred to as libration points, are not mere mathematical curiosities. They represent regions of gravitational equilibrium where the combined gravitational pull of the two larger bodies and the centrifugal force acting on the smaller body cancel each other out. Lagrange's identification of these points was a triumph of analytical insight, showcasing his deep understanding of the interplay between gravitational forces and orbital dynamics. The significance of Lagrange's work extends far beyond its immediate application to the three-body problem. His methods and discoveries have had a profound and lasting impact on astrodynamics and space exploration. The concept of Lagrangian points, for instance, has become invaluable in the design of satellite missions. Positioning satellites at these points allows for stable, fuel-efficient orbits, minimizing the need for constant course corrections. Numerous spacecraft have been placed in orbit near Lagrangian points, taking advantage of their unique gravitational properties to facilitate long-term observation and data collection. The James Webb Space Telescope, for example, resides near a Lagrangian point of the Sun-Earth system, providing it with a stable vantage point for observing the distant universe. Furthermore, the perturbation techniques pioneered by Lagrange remain essential tools in modern astrodynamics. These methods are widely employed to model and predict the motion of spacecraft, taking into account the gravitational influence of multiple celestial bodies. The accuracy and efficiency of these techniques are crucial for ensuring the success of missions that involve complex orbital maneuvers or long-duration spaceflight. Lagrange's legacy in this field is not merely one of historical interest. It is a living testament to the enduring power of his mathematical insights. His work continues to inform and inspire the design and execution of contemporary space exploration endeavors, solidifying his place as a foundational figure in the history of astrophysics. The precision and elegance of his analytical approach serve as a model for solving problems of extraordinary complexity, a testament to the lasting value of fundamental principles in the realm of scientific discovery. His work stands as a powerful example of the enduring interplay between pure mathematics and the practical challenges of exploring the universe. The elegance and power of Lagrange's analytical mechanics extend far beyond the celestial realm. His methods, initially conceived to unravel the intricacies of planetary motion, found fertile ground in diverse scientific disciplines. The principles of Lagrangian and Hamiltonian mechanics, direct descendants of his groundbreaking work, underpin our understanding of a vast array of physical phenomena, from the oscillations of a simple pendulum to the complex dynamics of molecules in a gas. These frameworks provide a powerful and versatile toolkit for analyzing systems governed by forces and constraints, offering a unifying perspective that transcends the specifics of individual problems. The ability to formulate equations of motion in a coordinate-independent manner, a hallmark of Lagrange's approach, introduced a level of abstraction and generality that proved transformative. This allowed physicists to focus on fundamental principles rather than becoming bogged down in the complexities of specific coordinate systems, greatly simplifying the analysis of otherwise intractable problems. Consider the impact on the study of fluid dynamics. The Navier-Stokes equations, which govern the motion of fluids, benefit enormously from the Lagrangian perspective. Tracking individual fluid elements over time, a technique readily facilitated by Lagrange's methods, reveals crucial insights into turbulent flows and other complex fluid behaviors. Similarly, in the field of electromagnetism, the Lagrangian formalism provides a concise and elegant way to express Maxwell's equations, simplifying calculations and revealing deep connections between seemingly disparate aspects of electromagnetic theory. The power of this approach lies not merely in its computational efficiency, but also in its capacity to expose the underlying symmetries and conservation laws that govern physical systems. It allows physicists to move beyond the mere description of phenomena and to uncover deeper, more fundamental principles. Lagrange's influence also extends to the realm of quantum mechanics. While his work predates the development of quantum theory by several decades, the mathematical structures he developed, particularly the concepts of generalized coordinates and conjugate momenta, proved remarkably adaptable to the quantum mechanical framework. The Hamiltonian formulation of classical mechanics, closely related to Lagrange's work, serves as a natural starting point for the quantization of classical systems, a process that underpins much of our understanding of atomic and subatomic phenomena. The transition from classical to quantum mechanics was greatly facilitated by the mathematical language and conceptual clarity that Lagrange's work provided. This transition demonstrates the remarkable longevity and adaptability of his ideas, proving that fundamental mathematical insights can have unforeseen and profound implications in entirely new areas of scientific investigation. What, then, is the enduring essence of Lagrange's legacy? It is not simply a collection of theorems and equations, but a profound shift in perspective, a testament to the unifying power of mathematical abstraction. Lagrange possessed a remarkable ability to perceive underlying patterns and to express them with an elegance and precision that continues to inspire generations of mathematicians and physicists. He demonstrated the immense value of a systematic and rigorous approach to problem-solving, showing how the development of suitable mathematical tools could unlock previously inaccessible areas of scientific understanding. His work is a powerful reminder that the pursuit of mathematical beauty and elegance is not a mere aesthetic exercise, but a crucial component of scientific progress. The seemingly abstract mathematical structures he developed have profoundly shaped our understanding of the physical world, providing the foundations for numerous advances across a wide range of scientific disciplines. His contributions extend beyond the purely theoretical. Lagrange was intensely aware of the practical applications of his work. He understood that the development of powerful mathematical tools was not merely an end in itself, but a means to acquire a deeper understanding of the natural world and to solve problems of significant practical importance. This practical orientation is evident in his contributions to celestial mechanics, where his methods were directly applied to the prediction of planetary motion, and in his work on fluid dynamics, where his analytical tools provided insights into the behavior of fluids that are still relevant to modern engineering challenges. The interplay between theoretical elegance and practical utility was a defining feature of Lagrange's approach to scientific inquiry, and this balanced approach remains a valuable model for scientists today. His influence extends even further, shaping the very way we teach and learn mathematics and physics. The Lagrangian and Hamiltonian formulations of mechanics are now standard components of advanced undergraduate and graduate curricula, providing students with a powerful set of tools for analyzing complex physical systems. His work serves as a testament to the enduring power of fundamental principles and the importance of a well-developed mathematical framework for understanding the natural world. The clarity and precision of his writing, coupled with the profundity of his ideas, have ensured that his contribution to scientific thought will continue to resonate for many years to come. In conclusion, Joseph-Louis Lagrange's impact transcends a mere catalogue of achievements. His legacy lies in the profound and lasting influence his mathematical innovations have had on scientific thought and practice. He showed the world the transformative power of a unified, elegant approach to complex problems, a legacy that continues to inspire and inform scientific and mathematical explorations today. His work stands as a testament to the enduring interplay between theoretical beauty and practical application, a powerful example of how fundamental principles can unlock previously inaccessible frontiers of scientific understanding, and a beacon guiding future generations of researchers toward new discoveries and deeper insights into the workings of the universe. The study of Lagrange is not simply the study of a historical figure, it is a journey into the heart of scientific progress itself, a testament to the enduring power of human ingenuity and the pursuit of knowledge. We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.